So, 8 lessons into acid-base chemistry. Math rears its ugly head again. When you have a weak acid, you do want to calculate how much hydrogen is it releasing, because the amount of hydrogen in the solution is what really determines the pH and what we call the acidity of the solution. So, if we're given something like this, 0.3 moles per liter hydrosulfuric acid, the formula we have here tells us that the H3O concentration for it, if you want to write H plus, that's fine. I usually go H3O, but it varies, equals the square root of Ka, which is the acid constant for hydrosulfuric acid, which you can find in the data book. H2S is about halfway down the second page. It's a relatively weak acid, and its acid constant is 8.9 times 10 to the minus 8, according to the 2010 Alberta Ed data book. So that's our Ka times square brackets like this mean the concentration of, so this means the concentration of our acid, which is 0.3. And out comes the calculator. 8.9 times 10 to the negative 8 times 0.3 gives 2.7 times 10 to the minus 8. And then we square root that and get the H3O concentration as 0.0001634. And that's a concentration, so it's in moles per liter. We're only, I was going to say we're allowed 3 significant digits for this, but we're actually only good for 2 because of this acid constant. Anytime you pull out a Ka from our data book, you're probably getting 2 sig digs, and so 0.00016 moles per liter is really where we should have stopped. Well, let's get on the side of righteousness and lose that 4. Okay, so that's how we're going to do all of these. This formula is fine, but this one is set up for finding H3O. As long as they're asking for H3Os, I think I will prefer this one most of the time. I'll do one with the Ka formula just to prove that it works. What is the H3O concentration of blah, 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 propanoic acid? So the acid constant of propanoic acid is, rapidly scan the data book, I get 1.3 times 10 to the minus 5. 1.3 times 10 to the minus 5. I'm using this now, so Ka equals the H3O concentration, which I don't know yet, and that's squared, divided by, and the acid concentration is 0.0144. So if we're trying to algebra this, we want to get this 0.0144 out of the denominator, so we multiply both sides by it. Actually show that. 0.0144, and same thing on the left, 0.0144. These on the right cancel out. And so our next step looks like H3O squared equals 0.0144 times 1, whoops, sound of me messing up on the calculator. Okay. My calculator runs out of space to display this, so I get 3 times 10 to the minus 9, which is a pretty lame value. I believe it's holding more sig digs than that in memory, it just can't show them to me. Now, we want H3O alone, so to strip the square off it, we square root both sides, and from that we get H3O equals 5.192, or I'll round that to 5.2, times 10 to the minus 5 moles per liter. If you run this with the root Ka times acid formula, I believe you'll find the same result, because look what we did. We took our Ka here, we ended up multiplying it by the concentration of the acid, and then we square rooted the result. We did exactly what this formula says, it's just we did it on our own algebraic initiative instead of just following the steps here. So These really are equivalent. You can feel good about either one of them. Okay, I'm going to pick up the speed a little bit and let's hammer through the rest of these. Okay, concentration of ammonium ion, H3O equals root. Acid constant for ammonium is 5.6 times 10 to the minus 10 times 0.0758. Put a times symbol in there. And 0.0758 square root. I get 6.5 times 10 to the minus 6. This calculator doesn't go to scientific notation, so I get to do it myself. Poor me. Hydrocyanic acid. Oh, okay, now they change it up. Our formula says H3O equals root Ka times the concentration of the acid. Now look what they give us here. They tell us the H3O concentration. They just hand it to us. It's 1.114 times 10 to the minus 5. And our formula says that must have come from doing the acid constant for HCN, which is 6.2 times 10 to the minus 10. Times the concentration of the acid, and I don't know what that is. They're asking us to find it. So instead of just running the formula as written, we have to do some algebra and get the HCN out of here. First problem, the HCN is buried under a root sign and we want to strip that off. What's the opposite of square rooting something? Squaring it. If we square that and we square the right side, this square and the square root will kill each other. Those are just gone, leaving us with 6.2 times 10 to the minus 10 multiplied by the acid concentration. If you just want to call this X or something, go ahead. I'm writing HCN, but there's not a lot of benefit to that. On the left side here, I have to do 1.114 times 10 to the minus 10, and I have to square that, which gives me an itty-bitty number. 1.241 should be enough, times 10 to the minus 20. Now, if we want HCN alone, we have to get rid of this 6.2 times 10 to the minus 10, so we divide both sides by that. 6.2, sorry, getting illegibly small. We divide both sides by 6.2 times 10 to the minus 10. 6.2 times 10 minus 10. And that lands us on the HCN concentration being 2.0 times 10 to the minus 11 moles per liter. Pretty watery solution.